Welcome to AP Chemistry at Hondiga High School. Today we'll be looking at our last part of notes over our chapters about atoms and elements. And we'll pick it up with section 21.4, getting into radioactive decay. And here's where we get into some of our major math that will be on this test. Now, the rates of decay of nuclei are commonly expressed in terms of half-lives. This is really a way to kind of dummy down the situation to make it easier to understand what's happening. So when you say, after one half-life, it makes it mathematically easier to understand, okay, well then half of it's going to be left. So a half-life is the length of time required for half of a sample to decay or react. And this is what a typical decay first order reaction looks like. So what you're seeing here for the decay of cesium is pretty much what any of them would look like. The difference is when the time at what time do you actually hit your half-life? So really the only thing that's going to change much here is what these numbers are down there. Now, how much cesium-137 will remain after 3 half-lives? Remember, in terms of half-lives, you're really counting how many times you have to divide by 2. So if we start with 100% of our sample after 1 half-life, we're down to 50%. After 2 half-lives, we're down to 25%. Divide that by 2 again, and after 3 half-lives, we're at around 12.5%. Now, if you knew how many years a half-life would take, you could then you could find out how long it would take if you knew you had 50 grams. After 1 half-life, you'd be down to 25. After 2 half-lives, you'd be down to 12.5 grams. After 3 half-lives, you'd be half of 12.5, 6.25. So depending on what information you're starting with, if you're just dealing in terms of how many half-lives, it's a fairly simple math. And that's why we go with the concept of half-lives, because it's a much easier way to do math in general with some of these simplistic situations. Now, to go beyond the half-life, what if you're not exactly at a half-life? What if the half-life is 50 years and we're talking, not multiples of 50 years? Then the math gets a little bit trickier and we need an equation to do that. Well, and at its heart, all radioactive decay is actually what's known as a first-order decay process. Now, the kinetics of such a process, we're back in chapter 14, and they obey the equation that looks like this. The book gives us this as the natural log of nt, so how much do we have left at time t, over the n0, which would be, what was our amount at time 0, and that's going to equal negative kt, and k is actually a constant, and t would represent the time. Well, this is the equation. It was introduced in chapter 14. Remember, we're looking at chapter 21 here. So in terms of actual where this comes in the book, technically by the time we got here, we would have done some reactions dealing with different types of kinetics. Now, the nice thing is here is it's all first order kinetics. When we get into chapter 14, we'll see, well, sometimes zero order, sometimes first order, sometimes second order. Radioactive decay is always a first order, so there's no choice about an equation. We're just going to use this equation for any of our calculations. Now, remember on your AP constant sheet, there are some equations. Well, in what form does that equation appear on the constant sheet? Well, it would be the natural log of AT minus the natural log of A naught would equal negative KT. Now, these two equations are equal to each other. They're expressing the exact same thing. Remember with log math, because I know over the past couple of years you've done some log math, um, dividing in log math is subtracting. And so these two are fundamentally the exact same expressions. Now, you have used in math class in the past week, um, and I'm pretty much, if you were in Mr. Hearn's class um, or Mr. Hart's class, I think within the last week and a half, you've done half-life reactions and you've used equations. As long as you're dealing with a first order reaction, the equation may look different, but it's the exact same equation. So this is what you're going to see on the AP constant sheet. And this is what I typically teach from, because I want you to be using and be familiar with what you're going to see on the sheet. But if you're using an equation that's the exact same thing, it just looks different, your math is all going to end up the same and it's all going to end up valid. So remember, you do not have to use this. If you want to use the equations that you're learning in math class within the last week and a half, go right ahead. You're going to get the exact same answer. I just typically teach from the point of view of what you're going to see on the AP constant sheet. So we basically have two different forms of the same equation. This is the form your book often uses, and this is the form that I quite often use for looking at the same thing. Now, NO is the initial number or the initial amount, and it could also be the initial mass. So these two things are used interchangeably. And it can also deal with the amount of disintegration, sometimes that's what it's referring to. So how fast is it decaying? So the number of disintegrations is also proportional to this. So we can use a number of different numbers, and we'll look at that in the calculation in a second, how that would work with something rather than the amount in terms of the mass or the actual number of particles. So N and A are interchangeable here. N would represent the actual number of particles, and A would represent the mass of those particles. But the T and the O, same exact thing, and the calculations will work the same exact way with the same exact equations for both of them. And remember, T would be our time interval. How long was this decaying? Now, at half-life, and we refer to half-life is T sub 1/2. So whenever you see this anywhere, know we're talking about the half-life. Well, if we're at 1 half-life, which would be the length of time it takes for half it to disappear, then the amount that we have left is going to be half of what we started with. So after half-life, we're going to have half the number of particles or half the mass, or now it's going to be disintegrating at half the rate. All those things are related to each other. So remember, at a half-life, we have half of what we had before. Now, if we substitute into this equation above, remember, I'm looking at the equations in the book because I think it's easier to see the math this way, and this is how it describes this in the book. But we can get the same thing with the other equation as well. So if you plug these into either equation and solve, you're going to end up with this equation. Now, this is one of those equations where it's not on the AP constant sheet, but it's one I think you really, really should know. It's a quick, easy way to typically calculate K. That's typically what we use this equation for. Now, if we knew what K was, and K is going to be a rate constant for the reaction, we could also calculate what the half-life is. But all we're really doing is substituting this idea into this equation up here, and that equation is going to simplify or reduce to 0.693 over K equals T half-life. And this is not on the constant sheet. And yes, you can take what's on the constant sheet. You can take this equation right here that's in black, that's the one that's on the constant. You can plug in the numbers and get the exact same thing. So you could say, okay, this is going to be 1, and this is going to be 1/2, because that's what's going to be left after 1 half-life. And you'll reduce to the exact same thing we just got. You would get that's going to equal 0.693. So that would mean I should say negative 0.693. So that would mean 0.693 over K would equal T 1/2. Because if we're at our half-life time, we're no longer talking about T, we're talking about T 1/2. But that is a very, very useful equation to know and use. So this is one I really recommend you know. And yes, you can do a quick substitution from what's on the constant sheets to derive it if you so wish, but it's just easier to know it. So if you know the half-life, you can solve for the decay constant K. And that's typically one of the first things you'll do in a problem is they tell you the half-life. You need to know, okay, that means I can find K. So whenever you see the half-life, what you're going to be doing is solving for K. Now, by substituting the amount of the radioactive nuclide present at any given point in time with the amount normally present, then you can use the following equation to actually determine the age of the substance. So in other words, we can take that same equation which I showed a second ago and solve it for T. So once we know this, if we're given these bits of information, we can calculate how long it took to get to that point. In other words, if you knew how fast carbon-14 decayed, what its half-life was, and you knew how much you had now, and you knew how much you would have started with, so what percent of stuff is left, and at the beginning, obviously, you'd have had 100% to start with, you can actually calculate how old something is. So how long did it take to get to this point in my decay cycle? And that's where carbon-14 dating comes in. Now, another equation that's given on the AP constant sheet right by this one. So this is a warning, be careful. Never, ever, ever in this chapter go to use this equation. This is the equation for a second order decay reaction. All radioactive decays are first order reactions, so this is not appropriate for anything we're ever going to be doing in this chapter. I know you're going to see some of the same things. You'll see this, and you'll see this, and you'll see those. Do not use this equation on this test because that's not appropriate to what we're talking about with half-life decay. Now, here's an example of a half-life problem. So this is going to be a decay problem. Now, A wooden object from an archaeological site is subjected to radioactive or radiocarbon dating. The activity of the sample that is due to carbon-14 is measured to be 11.6 disintegrations per second. In other words, when something decays, whether it's an alpha decay or a beta decay or whatever, every time a particle decays, then an alpha particle or beta particle is going to be spat out. So you can come up with a way to measure how fast at this point in time is it disintegrating. And that's what really this is talking about. The activity of sample is how fast is it decaying. And this is an important idea. For every one nuclide that decays, you get one alpha or beta particle, depending on the type of decay, coming out. So for every particle decaying, you're going to get one particle coming out. And in this particular case, how fast is it decaying? Well, it's 11.6 disintegrations per second. That's known as the activity. Now, the activity of a carbon sample of equal mass from fresh wood, in other words, if we had the same mass of wood and it was fresh and it decayed at 15.2 disintegrations per second, we would know at one point what should have this sample been disintegrating at, and at what point is it disintegrating right now. So what we really have here is analogous to this is our N0 and this would be our N at T. So this is what it used to be doing and this is what it's doing right now. This used to be its mass, its number of particles. This is the mass or number of particles I have now. So what they're really telling us is information that we can plug into that initial at zero time and at time t type numbers. Now, notice the next thing they tell us is the half-life of carbon-14 is 5,715 years. And I just mentioned this a second ago. Whenever you see this, that means do what? Think about what I just talked about. Whenever you see the half-life, that means find K, because we're going to need to know K to answer the question. So what is the age of the archaeological sample? So this is how fast it's disintegrating right now. This is how fast it really should be disintegrating if it was a fresh piece of wood. So first we need to determine our rate constant. Where I said, you see half-life, find K. You see half-life, find K. You see half-life, find K. And that's why this equation is so convenient. It's a quick way to get K. So if our half-life was 5,715 years, divide that into 0.693, and we know our K value is 1.21 times 10 to the negative fourth, and that would be our rate constant. And its unit would be per year. So 1 over year or year to the negative 1. All those are both all valid ways of expressing it. And watch your units on these things. Now, like always in AP chemistry. So now that we've got our K value, we can go back to original equation. Notice I'm using the one in black, the one that's going to be on your AP constant sheet. So I'm going to use it in this form rather than the form they show in the book, just so that you're practicing it as you would practice it if you're using the equation on the sheet. Um, you take your K value, which we've got right here, and you plug that in. Now remember, at current time, this is how fast it was disintegrating. So that's our at time t. And what it would be at time 0 was 15.2. That goes in there. Take the natural log of both of those, subtract, and you find out that this sample of wood, the the object that the wood was made of, it was a tree 2,230 years ago, and that tree was cut down and manufactured into whatever article it was. So what we're really finding out is at what point did the tree die that the wood came from? And in this case, it would have been 2,230 years ago. Now, another thing that pops up that unless you see it, you tend to struggle with, and it's related to dealing with the number of decays. If you know how much your mass changes over time, so we know we used to have 12 grams and now we've got 11 grams. So 1 gram of our old substance decayed away. And remember, it's 12 grams of cobalt 60 and now we only have 11 grams of cobalt 60. So it's not looking at the total mass of the sample, it's looking at the mass of a particular isotope, what it was and what it is now. Well, if you know how much the mass changes, remember mass is related to moles. So if you know the substance, and this happens to be a calculation for cobalt 60, if you know the mass, then you can find out how many moles you've got. And if you know how many moles you've got, you can find out how many particles you've got. So if you know how much of your mass decayed, then you know through simple dimensional analysis using molar mass and Avogadro's number, you know how many atoms decayed. And remember, every one atom decaying is one disintegration. In this case, it would be one beta particle. So every time a atom decayed, it released, in this case, since it's a beta decay, it would release a beta particle. If it was an alpha decay situation, for every atom that decays, you release one alpha particle. So remember, it's a one-to-one situation. So every decay is one disintegration. Every decay is one beta or alpha particle coming out. Now, next session gets into detecting radioactivity because remember, radioactivity is invisible. So how can we detect it? Well, one way is you can use a Geiger counter to measure the amount of activity present in a radioactive sample. So how fast is it releasing radioactive particles? Now, the ionizing radiation that occurs when a particle decays and an alpha or beta particle comes off, that will create ions. And because you now have ions, you can conduct electricity. So what you can really do here is basically have a gas, and as these high-speed particles come out of your decay, that will cause the gas to ionize, which will make the gas conduct electricity a little bit more. And as more decays occur, the more you can do. So literally, by looking at, is it when a decay happens, you're going to cause a flow of electrons and it can detect then basically or count every single decay that happens. So because the ionizing radiation comes off, can create ions in the gas, and now it will conduct electricity. You can use the flow of electricity to literally count how many decays you've got. And in a nutshell, long and short of it, that's simply what a Geiger counter does. If you've ever heard a Geiger counter, it's clicks. That's a sound that's telling you a disintegration occurred. Now, the next section is another type of math related to the chapter. And this is something I talked about a little bit in some of the classes based on some of the questions we had. And it's related to, remember, the mass deficit or mass defect in an atom. There's a tremendous amount of energy stored in the nucleus to help hold those protons together. And Einstein's famous equation E equals mc squared is related directly to the calculations for this energy. So in chemical reactions, any type of mass change that occurs is so small it's not measurable or minimal. But when we have changes in nucleuses, now we're talking about a much greater amount of energy, which means a much greater amount of mass, so it becomes measurable. To calculate the energy change, if the mass change for decay of 1 mole of uranium-238 was 0.0046 grams. So we've got some decaying uranium, and we end up with a mass change of 0.0046 grams. We can use Einstein's equation to actually calculate how much energy that would be. So the change in energy would be literally the change in mass times the speed of light squared. In this particular case, our mass changed by 4.6 times 10 to the negative 6, and it was going down by that much. If we multiply that by our speed of light, and remember on the constant sheet, you're going to see this is 3.0 times 10 to the 8th meters per second. Since we're in kilograms, remember you got to be in kilograms, not grams. So notice that change. Watch your units, watch your units, watch your units. If we're in kilograms, meters, and seconds, we get to joules. So we can actually calculate what that amount of joules would be. And one place where this was used is in finding out the energy or the nuclear binding energy based upon the mass defect of an atom. So in 1930, scientists discovered that the mass of nuclei are always less than the masses of the individual nucleons that make them up. And this is something we talked about in class on a previous day. Well, that difference in mass is known as the mass defect. And what was happening, if you take a look, this is what, so if we have helium, helium-4 basically. It's two protons and two neutrons, and if we add those particles up, that's what the mass should be. But if we actually mass helium, we end up with this mass. Well, there's a difference. Why do we have that difference? Well, the mass difference is our mass defect. That's the nuclear binding energy. So that's the mass lost to surroundings as energy when the nucleons were bound together, lowering the potential energy and making a more stable situation. So you could use that to actually calculate what that nuclear binding energy is. Now, the larger the binding energy, the more stable the nucleus. And binding energies increase as the mass number increases, and then they peak around 50 to 60, and then they slowly decrease after that. Now, when you look at this, one thing that some students will say is, Mr. Brown, you've said time and time again that higher potential energy is less stable, lower potential energy is more stable. This seems to go against that. What you're saying is if this is around the most stable atoms, now it's increasing. in energy and it's becoming more stable. That doesn't make any sense whatsoever. Well, that's because this is the binding energy per nucleon graphed against the mass number. If we look at it from a slightly different point of view, because this looks like higher energy that should be less stable, and I'm saying it's most stable somewhere around 50 to 60, and then slowly becomes more less stable after that. Well, if we actually rearrange it and look at the bond potential energy per nucleon, so we're talking about the energy from a different point of view. Now you'll see we get a graph where clearly we're dropping in energy and the lowest spot is going to be somewhere around here, and therefore that would be a more stable substance. So typically something like iron atoms are more stable substances. So if you take a look at what the cores of planets are and so forth, that can be related to which particles are most likely stable. So this really is look like is that from a stability point of view. So here you can see that's where your stability basically is most, somewhere around 50 to 60. And then remember, once you get above that, you're getting too large of a nucleus then, and your stability is going to get less and less and less until you get around 83, and it's just not stable anymore. So what this really says is the smaller atoms and larger atoms, those things are actually less stable than things in the 50 to 60 atomic number range. And that's exactly correct. Now, why is it increasing here at the beginning? So why does that go up? And why does this go um, uh, up? Well, remember, you've got more proton to proton repulsion. So that's why when we look at it from a binding point of view up here, so this question is really related to our top graph. When we're looking at it from a binding point of view, why is it going up? Well, we're getting more proton to proton repulsion. Now, next section gets into fission and fusion. So some harnessing nuclear energy and nuclear reactions in the world around us. So how do we tap all this energy that's inside the mass that we could unlock when we mess with nucleuses? Well, one way to do that is with fission. Remember, fission means to break. So breaking a large atom to release energy. Nuclear fission is a type reaction that's carried out really in nuclear reactors. So what happens at BBrown to generate energy? It's a fission reaction. And the secret to fission reactions is this is what starts. So a neutron comes in and hits our uranium-235, and it will cause the 235 to fission into these two possible reactions. So we actually have two side reactions that can happen, excuse me, that can happen here. But the key to what makes this special is when one neutron comes in and hits uranium-235, notice it creates more than one neutron. Well, those neutrons can go and hit more uranium-235 and keep the reaction going. So the secret to fission reactions, nuclear power plants, and even nuclear bombs is the fact that we can actually get a reaction that builds. So what starts the reaction actually gets created again in greater number so the reaction can multiply. And we can go from relatively few numbers to reactions to a large number of reactions in a very short period of time. And what we're really looking at here is this situation, how one can make two and then two can make four and so on. So the bombardment of a radioactive nuclide with a neutron can start the process. And as more neutrons get released in the transmutation, because remember this is an induced, we're making this reaction happen. That's going to cause the decay and you're going to get more neutrons. And that process continue to grow until we get what's called a nuclear chain reaction. In other words, pushing over one domino will keep other dominoes falling over and over and over and over. And it will build. It gets larger and larger and larger. So we're getting greater amounts of energy. Now, if there's not enough radioactive nuclides in the path of the ejected neutron, then the chain dies out. So to really get this reaction to go, we have to have enough nuclides relatively close together to sustain this chain reaction. And if we really want to get a nuclear bomb, an out of control expanding chain reaction, we have to have them incredibly, incredibly close together. And one of the things that we found out in creating nuclear bombs was, when you have a pure sample, that's just not close enough. It's not dense enough. The particles aren't compact enough. So if we want a nuclear bomb, an expanding reaction that takes place, within a split second and gets out of control and releases massive quantities of energy, then we have to get these things compressed and forced very, very, very close together. So therefore, there must be a certain minimum amount of fissionable material. That, like in the case of uranium-235, you got to have enough uranium-235 close enough together to get the chain reaction going and make it sustained. And that's what's known as a critical mass. So if you've got enough close enough together that when you push over the first domino, your dominoes will keep falling, you have what's called a critical mass. Now, if you want a supercritical mass, that's basically when the chain reaction not only keeps going, but it keeps going and keeps accelerating and very, very rapidly gets large and out of control. That's what happens in a nuclear bomb. In a nuclear power plant, while you have a critical mass enough to keep the chain reaction going, there isn't enough fissionable material close enough together to get the supercritical mass, the out of control, expanding, accelerating chain reaction. So, can Byron explode like a nuclear bomb? No, it can't. Can it explode? Yes, because it's big, basically a big steam generator. So yes, that creates pressure, and if it gets hot enough, you could have an explosion. It's just not a nuclear explosion, but this can still be dangerous because then you can spray the surrounding area with radioactive material that would normally be contained at the site. And also, if your fail safes break down, that critical mass can keep creating energy, and that can, literally cause all kinds of problems at the site in terms of, melting the reactor or other types of things. But no, it's not going to explode like happened at Hiroshima and Nagasaki. You're not going to get a nuclear explosion because you don't have a supercritical mass. Now, in nuclear reactors, the heat generated by the reaction is usually, and this is what happens at Byron, is used to produce steam, and that turns a turbine. So it's basically a big steam generator. It's just our nuclear reaction is the energy we use to make the steam. Now, the reaction is kept in check by the use of control rods. Remember, neutrons are what hit other things and cause the reaction to occur. So if we can steal the neutrons, then we slow down the reaction. Not having enough fissionable material would cause us the reaction to slow down. But the problem is, in a nuclear power plant, we want enough fissionable material. So how do we control it? Well, if we have rods that basically steal neutrons, then they will slow down the reaction. And you can speed up and slow down how much energy is coming out of the nuclear reaction by raising or lowering those control rods. Now, another process, and this is the last section that we're going to look at, that can release energy is nuclear fusion. Now, fusion is the energy released when light nuclei are fused together into heavier ones and release energy. So fission is breaking large material to get energy. Fusion is fusing smaller particles to get energy. In both cases, you end up getting energy. Now, fusion is basically where all of our energy in Earth has come from because it's all come from the sun, and the sun is a massive fusion power reactor. The problem is, you could also say, well, we've never used fusion on Earth to get energy um, outside of maybe a fusion type bomb uh, because we can't keep a sustainable fusion reaction going. So, indirectly, all of our energy came from the sun, and that was a fusion reaction. But we have no sustainable fusion reactions on Earth that we're doing to create nuclear power and to create electricity for people. But the sun really is a massive fusion reaction, and that's really where the energy coming out of the sun comes from, is that fusion reaction. Now, fusion would be a superior method for generating power because you get more energy, and the byproducts, the waste that you get, are significantly safer than with a fission reaction. The problem is, um, we can't really get that sustainable expanding reaction like we get with fission. And the material is so incredibly hot. How do we contain it? Because it's millions of Kelvin in temperature. So the good news is it would be better. The bad news is we can't really create a situation to get a sustainable fusion reaction and contain it because of the temperatures are so incredibly hot. So a tokamak type of apparatus like the one shown at the right is showing potential promise, and what they're really using is magnetic fields to create a magnetic bottle to hold reactions that are happening at millions of Kelvin temperature. But right now we don't really have any functioning reactors that generate in a sustainable way and controllable way energy using that. Well, that ends our notes over the atom and the molecule.